So in the last class, we had discussed about the amplitude modulation, okay, amplitude modulation and PSC, and then we discussed about the SSB, okay. So all these three is a modulation where we change the amplitude of the carrier to modulate the carrier, okay. So the amplitude is a function of the message, and because of that, the amplitude gets modulated of the carrier. Now we will go through the another kind of modulation, that is the angle modulation, where we change the angle of the carrier with the help of the message. Okay. So this has a two type. One is the phase modulation and another one is the frequency modulation. So we will see what is the difference between this phase modulation and the frequency modulation. I will just quickly go through what is the difference between the phase and the frequency. So the frequency is given as the derivative of the phase, okay? Or you can say that phase is integration of the frequency, okay? So frequency has two way to represent is. First is the radian per second, which is omega, and second one is the hertz, which is f, okay? So there is a relationship between f and omega. Omega is equal to 2 pi f, okay? So that's why when you write it omega t equal to d theta by dt, you don't see any 1 by 2 pi here. Okay. So the this frequency in radian per second is equal to the differentiation of the phase, or you can say that the phase is equal to the integration of the frequency. Now this ft or omega t or all this theta t is instantaneous value of the phase and the frequency. Let me go to the next slide. So first is the phase modulation. So in the case of phase modulation, the phase of the carrier gets modulated such that the phase of the carrier is changing. Okay. So here the phase of the carrier is proportional to the message. Okay. So you see this is the kind of frequency. This is a carrier frequency omega ct. And other than that, we are getting this extra term, which is Kp into Mt, where Kp is some constant and Mt is the message. So you can say that the theta t is proportional to the Mt. Okay. So in the case of phase modulation, the phase of the message is proportional to the message. Okay. So phase of the carrier is proportional to the message. Okay. So once you replace this theta here, you'll get the phase modulated signal as A cos omega ct plus kpmt. Okay. Now the unit of kp will be equal to the radian divided by the unit of the mt. Okay. If mt is unitless, it will simply be the radian, and if mt is, let's say, volt, then in that case it will be radian per volt. Okay. Now here you need to be careful about the unit of the kp. Okay. Here I have assumed the unit of the kp to be radian, but in some question the unit of the kp can be hertz. So in that case, you need to change this hertz to the radian per second. So okay, so you should use this formula if kp is radian per second, but if it's kp is given as a hertz, in that case the phase modulated signal will be given as cos omega ct plus 2 pi kp into mt. Okay. In this case, this kp is in hertz, this is in hertz, and once you multiply it by 2 pi, this complete thing becomes radian. Okay. So if the kp is given as a radian, we can directly use this, but if kp is given as a hertz, we have to multiply it by 2 pi to make it radian. Next is the frequency modulation. In this case, the frequency of the carrier is proportional to the message. So in the last slide, the phase of the carrier was proportional to the message. In this case, frequency of the message is carrier is proportional to the message. Okay, that is the difference between the phase and frequency modulation. In the case of phase modulation, the phase of the carrier is proportional to the message. In the case of frequency modulation, the frequency of the carrier is proportional to the frequency of the carrier is proportional to the message. Okay. Now we know that there is a relationship between omega t and the theta t, and that is the if when you integrate the omega t with respect to t, you will get the theta t. Okay. Now if you put this omega t here, okay, this which is omega c plus kf into mt, and integrate it, you will get omega ct plus kf integration of the mt. Okay. So in the last slide, when we discussed about the phase modulation, there the phase was proportional to the message. In this case, phase is proportional to the integration of the message. That is the difference between the phase and frequency modulation. So now, in this case, the modulated signal will be given as A cos omega ct. So this is like completely theta t, and this is complete theta t. We are just replacing this theta t with this term, which is omega ct plus kf integration of mt dt. Now in this case, the unit kf is radian per second. Okay, its unit will be radian per second if mt is unitless, but if mt has some unit, and let me again assume that its unit is volt, in that case the unit of kf will be radian per second volt. Okay, so that is the difference. So in the last slide, when we discussed about the kp, the unit of kp was just a radian. In this case, it is radian per second. Okay. Now again, in this case, if kp is given as a hertz per second, okay, in that case, we need to multiply this complete thing with 2 pi to make it radian per second. Okay. So that is the that the difference will come when unit is difference. Okay, so as of now, I am assuming that the unit is radian per second, but if it is different, then we need to multiply it by 2 pi here. Now let's go through what is the instantaneous phase and the frequency. So instantaneous phase, in the case of phase modulation, will be directly written at like this. We know that phase is proportional to the message, and we know that the theta t is equal to omega ct plus kpmt. This is what we call it as an instantaneous phase in the case of the phase modulation. In the case of frequency modulation, the instantaneous phase will be given by this. Okay, so you see the difference here. It is proportional to mt, and in this case, it is proportional to integration of the mt. Now, when it comes to instantaneous frequency, we know that the frequency is equal to the derivative of the phase. So in the case of phase modulation, the frequency will be given as you just take this phase and do the derivative with respect to t. So when you take the derivative of this, the instantaneous phase will be given as, sorry, frequency will be given as omega c plus kp differentiation of mt. Okay, this is in the omega domain, which is radian. But if it is in hertz, okay, you can write it like this: ft is equal to fc plus kp d by dt mt, and there will be 1 by 2 pi because we are now writing in terms of hertz. Okay. Now in the case of frequency modulated case, again, to calculate the instantaneous frequency, we need to take this phase and do the derivative with respect to time. Okay. So when you take this phase and do the derivative with respect to time, you'll get omega t is equal to omega c kfmt. Okay. So in this case, in the case of phase modulation, the instantaneous frequency is proportional to the derivative of the message. In the case of frequency modulation, the instantaneous frequency is proportional to the message. Okay, that is a difference. And again, when you go from radian to hertz, it will be equal to ft, it is equal to fc plus 1 by 2 pi kf into mt. Okay. Go to the next slide. Now this is an important topic, maximum frequency deviation. And we will see the maximum frequency deviation as well as the maximum phase deviation and the modulation index. Okay, all these things are related. So we know that your instantaneous frequency is going to change with respect to message. It means that with respect to omega c, it is going to be up and down based on the message. Okay. So your instantaneous frequency can be at particular time instant can be higher than omega c, or it can be lower than omega c based on the value of the message. Okay. Now the maximum frequency deviation is given as the deviation of the instantaneous phase with respect to omega c, and when it is maximum, this deviation is maximum, that we call it as a maximum frequency deviation. So The case when this instantaneous phase has the most deviation with respect to this omega c, that we call it as a maximum frequency deviation. So this is in the case of the uh, so this is the general case. Now let's see what happens in the phase modulation and the frequency modulation. So in the case of phase modulation, we know that this omega t is equal to omega c plus kp differentiation of the mt. Okay, so this and this will cancel out each other, and the maximum frequency deviation will be given as max of the kp d by mt by dt. Okay, so this will be the maximum frequency deviation in the case of the phase modulation. In the case of frequency modulation, when I replace this omega t with omega c plus kf mt, again this and this will cancel out each other, and maximum frequency deviation will be given as max of kf into mt. Okay, so, or sometime you can also write it as a max of kf mod of mt. We can write it when kf is positive. If kf is some negative number, then you have to keep it mod here. If kf is positive, you can just take it out otherwise. Okay, so all this thing as of now is in omega. You can change it to f also, which is in hertz, and that means that you have to divide everything by 2 pi. Okay, so here we have 2 pi, here also we have 2 pi. Okay, so this is the maximum frequency deviation. Now in the case of phase modulation, the maximum frequency deviation depends upon the derivative of the mt. In the case of frequency modulation, the maximum frequency deviation depends on the absolute value of the message. Okay, so when the absolute value of the message is maximum, that point of time will get the maximum frequency deviation. In the case of phase deviation, when the derivative is the maximum, at that point of time will get the maximum frequency deviation in the case of phase modulation. Now let's see one question. So we have been given a message mt which is equal to sync 2000 pi t, and it is being frequency modulated with constant k. This k is actually the kf that we discussed in the last slide, is equal to 1000 hertz per volt. So you see in this case the k is in form of hertz, not in the form of radian. Okay, so this is 1000 hertz per volt. What is the maximum instantaneous frequency of the modulated signal when the carrier frequency is 1 megahertz? So we need to find out omega t max, maximum instantaneous frequency. Okay, we don't need to find out the maximum frequency deviation. We need to find out what is the maximum instantaneous frequency. So this is the instantaneous frequency, and we need to find out what will be the maximum value of this. Okay, and this is equal to omega c plus kf. In this case, it will be 2 pi into kf into mt. Okay, because kf is in hertz. Now, in this case, the option is given in the hertz. So instead of calculating the omega t, I will go for ft actually. So I need to calculate ft max, which is equal to fc plus kf mt. Okay, where kf is in hertz. Okay, so in the last slide when I did the derivation, I divided it by 2 because kf was in radian. In this case, kf itself is in hertz, so I don't need to do those division. Okay, so this is in hertz, this is also in hertz, this is volt, and this is hertz per volt. So everything will be in hertz here. Okay, once you do the calculation, everything will be in hertz. So ft max we need to find out. Now we will get the ft max when mt is the maximum. Okay, because fc is a constant, kf is also a constant. Now it all depends upon the value of the mt. So when the mt is maximum, we'll get the maximum instantaneous frequency. So you can write it as a 1000 kilohertz, which is fc here, plus kf is 1000. Now it is written it as a hertz here, divided by volt into mt. Now I can write this, we need to calculate as a mt max. Now mt is this sync, and we know that the maximum value of the sync will be equal to 1. So the maximum value of this message is equal to 1. Okay, and from here you can say that it is 1000 kilohertz, and this is in hertz. Once you convert it into kilohertz, it will be simply 1 kilohertz. Okay, this is 1, this is 1000, everything will be 1000 then after multiplication. And once you convert it into kilohertz, it will be simply 1 kilohertz. Okay, so you can say that it is equal to 1001 kilohertz, or you can say that it is 1.001 megahertz. Okay, so this will be the correct answer, option number D. Okay. So here we need to remember the difference between the instantaneous frequency, maximum frequency deviation, and so on. Okay. So all this thing we need to remember that what is the difference between the instantaneous frequency, what is the difference between the maximum frequency deviation. Now let's talk about the maximum phase deviation, and this we also call it as a modulation index. Okay, so whether it is the phase modulation or the frequency modulation, in both cases, the maximum phase deviation gives us the modulation index. So don't get confused that for the frequency modulation, the modulation index will be maximum frequency deviation, and for phase modulation, it should be maximum phase deviation. That is wrong. For both the cases, whether it's a phase modulation or the frequency modulation, the maximum phase deviation gives us the modulation index. So irrespective of the modulation, whether it's the angle, sorry, whether it's a phase or the frequency, maximum phase deviation will give the modulation index. Now, in this case, the maximum phase deviation we can calculate again by similar way, the way we calculated for the frequency. So maximum phase deviation will be given as the phase this phase omega ct with respect to the theta t. So what is the value of the theta t which gives us this value to be the maximum value? Okay. Now in the case of phase modulation, this theta t is equal to omega ct kpmt. Actually there is a t here, t is missing. So this and this will cancel out each other, and the theta t will be this delta theta will be equal to max of kpmt. Okay. Again, in this case, the maximum phase deviation will depend upon the value of the mt. In the case of frequency modulation, the maximum phase deviation will be given as omega ct, and this. So this is the theta t. This complete thing is the theta t in the case of frequency modulation. And again, we have t here. Again, t is missing here. So you just write t here, there is a t. This and this will cancel out each other, and this will be the maximum phase deviation in the case of frequency modulation. And again, this complete thing is in radian, and this is also in radian. Let me go to the next slide. Yeah. Now let's take a special case where we have a message signal, and message is a sinusoidal signal. Okay. So in this case, let me assume that the message is a AM sin omega mt. So this is the sinusoidal message. And let's see what happens to the phase modulation and what happens to the frequency modulation. Okay. So in the case of phase modulation, once you put this message, this will be the modulated signal. Okay. Now in this case, when you calculate the beta, which is the modulation index, which is also equal to the maximum phase deviation, and which is equal to max of kp into mt. Okay. Now in this case, this thing will be maximum when message is maximum, and the maximum value of the message we will get is equal to a of m. Okay, this is the peak value that we will get for the message. So in this case, the beta will be equal to kp into am. Now the maximum frequency deviation will be given as max of kp dmt by dt. Now once you differentiate this sign, you'll get the cos. Okay, we know that when you differentiate the sign, you get the cos. So let's put it here. Now we need to find out what will be the maximum value of this. So this will attain the maximum value when the cos is equal to 1. Okay, when the cos is equal to 1, the maximum value will be equal to kp am into omega m. Okay. Now, if you see this phase deviation and the max frequency deviation, there is a relationship, and that is that beta, which is equal to delta theta, will be equal to delta omega divided by omega m. Okay, because here you have kp into am, here you have a kp into am into omega m. Once you remove this omega m by dividing it, you will get the phase deviation. So phase deviation is equal to take the frequency deviation and divide it by omega m. Okay. Now let's go to the frequency modulation. In the case of frequency modulation, when you put this message here, you have to actually integrate it, because in the case of frequency modulation, modulated signal is given as omega ct kf integration of the message. So once you integrate this message, you'll get the, okay. So actually in this case, I have assumed the message to be equal to cos, okay. So once you integrate it, you'll get the sine here, okay, sine omega mt. Now in this case, when you calculate the maximum phase deviation, it will be equal to max of kf am omega m sine omega mt, and this will be the maximum. This will attain its maximum value when this sine is equal to 1, and when sine is equal to 1, the maximum value will be kf am divided by omega. Now the maximum frequency deviation will be given as max of kf into mt, and mt is am cos omega mt. So if you put it here, it will be like this, and again it will attain the maximum value when the cos is 1, and which will be equal to kf into am. So in this case, again, if you see the beta and delta of omega, there is a relationship that beta, which is also equal to delta theta, is equal to delta omega by omega. So this is for the phase modulation we checked. Same is true for the frequency modulation also, okay? That beta is equal to delta omega by omega m. Okay. In general, if the message has the bandwidth b, then the modulation index will be given as beta equal to del omega by 2 pi b, or del f by b. Okay. Here it is both of them are in radian. Here it is in hertz and hertz. Okay. Now this formula is applicable only for the low pass signal. If you have a signal which is kind of low pass type like this, where the bandwidth is b hertz, you can apply this formula. Okay. But in general, if let's say signal is not a low pass, it can be some band pass or high pass or any kind of those kind of signal. In that case, beta, you can write it as a delta omega divided by omega m, where omega m is the maximum frequency content. Okay, maximum frequency content of the signal, not the bandwidth, maximum frequency content. So for example, let's say we have a signal which is a kind of band pass signal. Okay, so let's say this is f1, this is f2, this is minus f1, this is minus f2. This is the band pass signal. If you see the bandwidth is equal to f1 minus f2 minus f1. But here when we calculate the modulation index, we should not put the bandwidth, we should put the maximum frequency content, which in this case is f2. Okay, so in this case the beta will be equal to delta omega by f2, sorry, omega 2 in this case. Okay, or beta is equal to delta f by f2. So this is all about the modulation index of the phase and the frequency modulation. Anyone has any doubt here? Okay. If no one is out, then let me go to the next slide. Okay. So let's see this problem. So we have a what is the modulation index of FM signal having the carrier swing of 100 kilohertz. Okay, and modulating frequency is 8 kilohertz. Okay, so here we need to understand what exactly this question is asking. So first thing is telling that FM signal having the carrier swing of 100 kilohertz. So what it means is that we have the FC, and this is the constant value. We have this FT. FT is the swing of around 100 kilohertz with respect to the FC. Okay, so this FT has a swing of around 100 kilohertz. Okay, so FC is a fixed value, and with respect to FC, it is going up and down based on the message, and that swing of this up and down is about 100 kilohertz. Okay, so this can go both up and down. So this 100 kilohertz swing is such that it is taking care of both going up and going down. Okay, so this FT will be going up as well as going down. Okay, So since it is 100 kilohertz swing, you can say that Ft mean will be something like Fc minus 50 kilohertz, and Ft max will be something like, so this is mean and this is max, will be something like Fc plus 50 kilohertz. Okay, because it is going up and down with respect to Fc by 100 kilohertz. So we can say that it is down by 50 kilohertz sometime and it is up by 50 kilohertz sometime. Okay? So this is the minimum and the maximum frequency of the carrier. Now, once you calculate the delta F, we calculate it with respect to the Fc. Delta F is equal to Fc, Ft minus Fc max. Okay, maximum frequency deviation. Okay, and maximum frequency deviation will be equal to 50 kilohertz, right? Not 100 kilo. That's the mistake people make here. It should be 50 kilohertz. This 100 kilohertz is both up and down. Okay, because of that, when you calculate the maximum frequency deviation, it is coming out to be 50 kilohertz. Now, it is being modulated by the signal which has a frequency of 8 kilohertz. This is talking about the message. So FM is equal to, or we can say maximum frequency content of the message is equal to 8 kilohertz. Okay. Now the modulation index is given as beta is equal to del F by FM. Okay. So the modulation index is given by del F by FM, which is equal to, so that del F is, we have calculated it to be 50 kilohertz. So 50 divided by FM is already given in the problem, which is 8 kilohertz. Okay, so this will be the beta, which will be equal to 6.25. Okay, so this will be the correct answer. C. Go to the next slide. Now, when it comes to the power of the angle modulated signal, unlike the amplitude modulated signal, in the case of angle modulated signal, the power is constant. And the reason is that the amplitude is constant here. It is the angle which is changing with respect to the message, not the amplitude. As since the amplitude is not changing, for the cos or the sine, we know that when you calculate the power will be given as the amplitude square by 2. Okay. So in this case, the case of angle modulation, the power is always equal to a square by 2. Regardless of what is the message we have, it will always be equal to a square by 2. So in the case of the amplitude modulation, the power of the modulated signal was changing with the message, but in the case of angle modulated, power of the modulated signal is constant. Let me quickly go through the spectrum of the FM. So a spectrum of the FM signal is kind of slightly complicated than the amplitude modulated signal. Okay, so here when you calculate the spectrum of the FM, here it is a kind of Fourier series. Okay, now the message signal here I am assuming to be a sinusoidal signal. Once it is sinusoidal signal, your modulated signal, you can write it like this. Okay, this is the modulated signal. Now, once you write this modulated signal like this, if you see this term, this is a periodic signal. This is a periodic term. And since this is a periodic term, you can calculate its Fourier series. Once you calculate its Fourier series, this is how it is going to look like. Okay, this A j omega ct I have kept it as it is, but the Fourier series of this is going to look like this. Okay, now if you see this term, this is the Fourier series of this second term. Now this term we call it as a Jacobian, Jk beta. Okay, now if you take this and take the Fourier transform of this, okay, this is what you will get. So this is actually S of f, not okay, wait, sorry. So this is the actually time domain signal itself. So this is the complex representation. Once you go to the real representation, you just take the real part of it and it will come out to be cos. Now when you take the Fourier transform of it, you'll get the impulse. Okay. Now we'll have an infinite number of impulse here ranging from k equal to minus infinity to infinity. And when you plot it here, this is how it is going to look like. Let's say for k equal to 0, you'll be getting J0 beta. And then del f minus fc and then f plus fc. Okay, so there will be one signal here and there will be one signal at minus fc, minus omega c. When you put k equal to 1, you'll get another impulse, you'll get another impulse, k equal to 2 and 3 and so on. Once you put it, you'll get an infinite number of them. So it looks like the bandwidth of the FM signal is infinity. So theoretically, the bandwidth of the FM signal is actually infinity. Okay? But we know that we cannot use the infinite channel bandwidth because the spectrum is very costly and we want to use it optimally. Okay? We want to use it optimally and efficiently. So because of that, what we do here is we consider only those parts which has a significant amplitude, and we just don't care about the part which has very less amplitude. Okay, so we'll see how to check whether so that story lies in the jk beta. If jk beta has a high magnitude, it means that the impulse will also have high magnitude. And if jk beta has a lower value, then impulse will have the lower magnitude. Okay? So when you plot the jk beta or jn beta with respect to the different value of the n, this is how it is going to look like. So if you see the higher value of the n, the value of the jn beta is very low. Okay. So because of that, we generally neglect this term while calculating the effective bandwidth of the FM signal. So if you see this, for a particular value of the beta, let me talk about the beta equal to, let's say, 3. For beta equal to 3, if you see this plot, this is the beta equal to 3 plot. After some value of the n, it is diminishing. So you can say that after the value this n equal to 4, this is kind of negligible. Okay. Similarly, for beta equal to 4, after n equal to 5, it is kind of negligible. And for beta equal to 5, after n equal to 6, it is negligible, and so on. Okay. So for a particular value of the beta, only a certain value of the n will have a significant value in the jn beta. Okay. And that we can say that for the k greater than beta plus 1, okay, or you can say n greater than beta plus 1, the j k beta or jn beta is negligible. And because of that, we will not care about those terms. We will just care about the term where beta plus 1 is less than k. Okay, so beta plus 1 is less than k. We will consider only, sorry, it is opposite actually. Beta plus 1 greater than k, or k is less than beta plus 1. So in that case, when you plot the FM signal, so we have the FC, we have one impulse till beta plus 1. Okay. So here we are changing the value of the k, and then here the k is equal to beta plus 1. Similarly, actually on the negative side also we need to care. Okay. So on the negative side also you'll get this. So the difference between these two is FM. So you have FM, 2FM, 3FM, and then beta plus 1 FM. On the negative side also, or I should not say negative, on the left side of this FC also you have this minus FM, minus 2FM, minus 3FM, and so on. Okay, with respect to the FC. So essentially, we are talking about this range. And in this range, the total number of impulse is 2 into beta plus 1. So the effective bandwidth will be given as 2 into beta plus 1 into FM. Okay, so this will be the bandwidth of the FM signal. In general, this formula is applicable for the PM signal also, so you can apply this formula for the PM as well. Okay. So bandwidth of the FM signal, or effective bandwidth of the FM signal, is 2 into beta plus 1 into FM. So theoretically, the bandwidth of the FM is infinity, but practically, since the jk beta is will be having very low value for the higher value of the n, we don't care about those terms. Okay. Now another way to write this is this one, because there is some relationship between the FM and the beta, which is beta is equal to del f upon fm. Okay. So another way to write this is this. Oh, wait, not this one actually. This is same actually. This formula is same. There is another way to write this formula is you replace this beta is equal to del f by fm. Okay, so once you replace this, the bandwidth will be given as 2 into del f by fm plus 1 into fm, or you can write it as a 2 into del f plus fm. Okay, so these two are the same formula, 2 into del f plus fm or 2 into beta plus 1 into fm. And the same is applicable for the PM signal. The PM signal, the bandwidth is 2 beta into 2b into beta plus 1 or 2 fm into beta plus 1, where fm is the maximum frequency content. Anyone has any doubt here?
No, sir.
Okay. Let me go to the next slide. So let's take a problem. So we have a sinusoidal, we have a again frequency modulation here, and the modulation index is given beta is equal to 2.4, and we need to find out what will be the bandwidth. So bandwidth is equal to 2 into beta plus 1 into fm. Okay, this problem is very straightforward. So beta will be equal to 2.4 plus 1 into fm. So this will become 3.4 into 2, 6.8 into fm. Okay, so this will be the correct answer. Let me go to the next slide. Okay. Now this is an interesting problem. So we have a phase modulated signal. So as I told, the bandwidth that we derive for the FM is applicable for the PM also. So I will use that same formula here. So we have a phase modulated signal with a frequency deviation of the 20 kilohertz. And the message signal that is modulating the carrier is single tone with frequency 2 kilohertz. So FM is equal to 2 kilohertz. So you can use any formula. So as I told, the bandwidth is equal to 2 into beta plus 1 into fm. So in this case, you need to calculate the beta by using this formula. Beta is equal to del f by fm. Or we can use 2 into del f plus fm directly, because del f and fm are given here. Okay. So I will use this. So 2 into del f is 20 plus 2. And this will give us the 44 kilohertz. Okay, so this will be the bandwidth of the FM signal, sorry, this PM signal. Now, if you compare this FM or PM with respect to the AM signal, okay, in the case of AM signal, the bandwidth was, if the message bandwidth was FM, the modulated signal bandwidth was 2 FM, just a twice of that. Or if it is B, it was 2B. Okay, if the message bandwidth is B, modulated signal bandwidth is 2B. But in the case of FM, you see that the bandwidth of the signal has a huge dependency on this beta, and beta is generally has this kind of value like 20 or like this kind of number. And because of that, generally the bandwidth of the FM signal is much greater than the bandwidth of the AM signal. Okay? So spectrum utilization in the case of the FM signal is very poor as compared to the AM signal. Let me go to the next slide. Okay. Now, a carrier waveform is this and modulated signal this. So this is our message. Have FC is equal to 100 kilohertz. So this is talking about this one. And FM is equal to 4 kilohertz. So FM is talking about this omega anywhere. Given that the sensitivity of the FM is 4 kilohertz per volt. So when it says sensitivity of the FM, here we are talking about the A of F, okay, which is also known as the sensitivity of the FM. Now here we need to be careful about the unit of the FM. Here it is given as a kilohertz per volt, not radian per second per volt. Okay, it is given as a kilohertz per volt. Now The FM spectra beyond J6, so this G is the Jacobian that we just discussed. So FM spectra beyond J6 is negligible. So what are the channel bandwidth requirement for AM and FM respectively? Okay. So in the case of AM amplitude modulation, the bandwidth is given as twice of the bandwidth of the message. And in this case, message is 4 kilohertz. So it will be simply 2 into 4, which will be giving us 8 kilohertz. So this option is wrong and this option is wrong. Now we need to find out whether which option of this B and C, sorry, B and D is correct. So for that, we need to find out what is the bandwidth of the FM. Now, in this case, as I told, so if you remember the spectrum of the FM, okay, it looks like this. You have one impulse at FC, one impulse at FC plus FM, then FC plus 2FM, 3FM, 4FM, going on. FC minus FM, FC minus 2FM, FC minus 3FM, FC minus 4FM, 5, 6, and so on. But we just need to care about the J till J6. That means that we need to just care about the J1, J2, J3, J4, J5, and J6. So this is FC plus FM. So this will be FC plus 2FM, 3FM, 4FM, 5FM, and 6FM. Similarly, here it will be FC minus FM, 2FM, 3FM, 4, 5, and 6. So we just need to take care from here to here to calculate the bandwidth of the FM. So if you see this width is FM, this width is FM, this width is FM. So if you calculate the entire width from here to here, it will be 12 FM. Okay. So that will be the bandwidth of the FM signal. So in this case, it will be 12 into 4, which will be 48 kilohertz. Okay. So in this case, this will be the correct answer and this will be the wrong. Yeah, if you see this problem, you see that the bandwidth of the AM and bandwidth of the FM, if you compare those, they are very different. AM requires very less bandwidth than the FM. Anyone has any doubt in this problem? Okay, let me go to the next slide. What bandwidth is needed for the FM signal that has a peak frequency deviation of plus minus 13 kilohertz and handles the audio signal from 200 hertz to 5 kilohertz. Okay. So if you see this problem, in this case, the frequency deviation is given as 13 kilohertz. Okay. And audio signal, so this is the message signal actually. This is the MD we are talking about. So MT has the frequency ranging from the 200 hertz to 5 kilohertz. Somewhere here. 200 hertz to 5K. Now in this case, if you calculate the bandwidth, it will be 500K minus 200, okay, which will give us the 4800. But as I told few slides back, when you are calculating the beta, okay, we need to care about, we should not take the bandwidth, we should take the maximum frequency control, and which in this case is 5K. So don't take 4.8K, take the 5K as a FM. So beta will be equal to del F by FM, where FM is 5K. So 13 by 5. Or we can use this formula also, that bandwidth is equal to 2 into del F plus FM. Okay. So this will also give us the correct answer. So in this case, del F and so FM is given as a 5. And wait, this is 13 or something else. I think 13. Okay. So it will be coming around the 36 kilo. I will check the option here. I am not able to. I think one of the option I might have not written correctly. So this will be 13 kilohertz here. Sorry, 36 kilohertz. Now let's talk about what is the wideband FM and what is narrowband FM. So first we'll talk about what is the narrowband FM. So any signal which satisfies this criteria is known as a narrowband FM. Okay, KF into ET is much less than 1. Or sometimes we also call it as a beta, which is a modulation index is much less than 1. So when this is the case, we call those kind of signal as a narrowband FM signal. Okay, so in the case of narrowband FM signal, there is some approximation that we can use, and once we have those approximation, we can try to design a circuit which can mimic those approximation. Okay, so this is the phase modulated signal, we know, and this term is much less than 1. Okay, this term is much less than 1. Now let's expand this. So this is cos A plus B. You can write the cos A cos B minus sin A sin B. Okay. Now we know that this term is much less than 1. So this is very close to cos of 0, which is equal to 1. Okay. This is actually kind of very close to 1. So you can just write it as a 1 and left with cos omega ct. For the second term, you have a sin omega ct and you have a sin kpmt. So if you know, remember the sin x, you can simply write it as a x if x is much less than 1. This is from the mathematics. So here kpmt is much less than 1. So this sin kp into mt you can approximate as a simply kp into mt and sin omega ct. Okay, so this is the narrowband FM signal. Now if you see this signal, you have a two sinusoidal cos and sine, but none of the sinusoidal has anything in the other than omega ct. It doesn't have any message dependency. It has just the sin omega ct and the cos omega ct. Message is now in the amplitude. So if you see this, it is very close to what we see in the amplitude modulation. Okay. So when you have this signal, which is kind of narrowband FM signal, we can take the help of the AM, amplitude modulated signal, to generate the narrowband FM. So how do we do this? So we know that this is the NBFM, NBPM signal. Okay. So this term, this MT into sin omega ct, we can generate it through the DSBSC modulator. Okay. We know that once you have a DSBSC modulator and input is message and this input is some sinusoidal, output will simply be the multiplication with some constant. Okay, and then you have a cos omega ct addition. So you just take this cos omega ct and add it here. This will give you the NBPM. For the NBFM, it is slightly different. So this is the NBFM formula where AT is actually the integration of the message. Okay. So what we do is that we just first integrate everything here and generate the AT, and then everything is same as what we saw for the PM phase modulator. Okay, everything is same here. And if you see this in this case, the generation of the NBFM is very simple. It is same as the AM modulator. Yeah. Now once we have this narrowband FM or narrowband PM signal where beta is much less than 1, there is a one method called the indirect method of FM generation. We can use this narrowband FM signal and generate the FM signal. Okay, so that circuitry that we use to generate the FM signal with the help of indirect method, we call this as a frequency multiplier. Okay, so here what the frequency multiplier does is when you have a, let's say, this signal and pass it through the frequency multiplier, it will multiply everything in the this argument of this cos by some number n. So that we call it as a frequency multiplier. Now, here if you see, when you do this kind of multiplication in the frequency and in the this and in this term also, what will happen to the beta? Okay. So let's say that for this signal, we had some beta. Okay. And the beta of this signal will be equal to kf am into omega m. Okay, if the message is a sinusoidal. Now, for the output, the beta will be given as n into kf am divided by omega m. Okay, so that is what is going to happen here. For the input, if you have some modulation index beta, at the output, the modulation index will get multiplied by n. And the reason is that we have this n term here. Okay, and because of this n term here, the beta of the output yt will be n times than the input st. Okay, so when you take this frequency multiplier and pass any signal through there, the output modulation index will be higher than the input if n is higher. And if n is very high, what can happen that if for the input, if beta is much less than 1, for output it can actually be the much greater than 1 if n is very high. Okay, so in this case it was a narrow band FM, but in this case it will become wide band FM or simply the FM signal. So this is what we call it as an indirect method. First, we will generate the MBFM signal through the circuitry that we discussed in the last slide, and then pass it through this narrow band, this frequency multiplier circuit to change the beta to be much greater than 1, and that will generate the wideband FM signal. So this we call it as an indirect method because here we are not directly generating the wideband FM. First we are generating the narrowband FM, and then through the frequency multiplier we are generating the wideband FM. Let me go to the next slide. Okay. Okay. So this is the indirect method. You have the message. First pass it through the narrowband FM circuitry, which is very close to kind of AM signal, AM circuitry. You get the signal where beta is much less than 1. Pass it through frequency multiplier. After the frequency multiplier, beta will become much greater than 1. So this complete thing we call it as an indirect method of the FM generation. Okay. Now this multiplier, this frequency multiplier that you see here, this thing can be designed with the help of any nonlinear circuitry. For example, diode. Diode is kind of nonlinear circuit. Similarly, BJT or MOS, all the circuitry can be nonlinear in certain voltage bias scenario. Okay. So those circuitry we can use for this frequency multiplication. So any nonlinear device. So for the nonlinear device, for example, let's say we have a yt equal to st square. So this is a nonlinear device. Okay. So the nonlinear device will have this kind of input-output relationship. This is the input, this is the output. Or it can do something like, let's say, yt equal to s to the power 4t or 5t, this kind of nonlinearity will be there. So in the frequency multiplier, we have a circuitry, which is a kind of nonlinear, and with the help of the nonlinearity, it is generating the multiplication in the frequency domain. Let me go to the next slide. Now let's talk about the direct method of the FM generation. So in this case, we use a circuitry, what we call as a LC oscillator. Okay, we have this inductor, we have this capacitor, and with the help of this inductor and capacitor, we are going to generate the FM signal. Okay, so this is the LC circuitry, and when you apply the voltage across this circuit, it will generate a current which will oscillate, and the oscillation frequency of that current depends on the value of the L and C. Okay, so omega, or you can say the frequency of this LC oscillator will be given as omega naught equal to 1 by under root LC. Okay, now let's say we have L, which is a fixed value. This is the fixed value, but we have a cap, which is a varactor. Okay, this varactor term you will see in the device. Varactor is a capacitor whose capacitance changes based on the voltage applied across this capacitor. Okay, so in this case, we will apply the message across this capacitor, which is a voltage. We will apply the message across this capacitor. So what will happen that the capacitance of this LC tank will change based on the message. Okay, so your capacitance can be written as C equal to C naught minus K into MP. Okay, so once you put this C here, the omega naught will be equal to this, or you can also write it like this, or you can also write it like this. Okay, it's just a rearrangement of everything. And now if K into empty divided by C naught is much less than 1, this complete thing you can write it like this. Okay. Now if you see this, the frequency of the signal in the LC oscillator is proportional to the message. Correct? And this is the behavior that we see for the FM signal. For the FM signal, the instantaneous frequency is proportional to the message, and that is the case here. The instantaneous frequency omega is proportional to the message. Okay. So in this case, the signal that will circulate through this LC tank will have an oscillation, and the oscillation frequency will depend on the message, and this will be the oscillation frequency. Yeah. Now you can write omega naught is equal to omega c 1 plus k into mt divided by 2 c naught, or you can write it as omega c plus kf into mt, where kf is all this constant k by k divided by 2 c naught. Okay. So this is the indirect method of the FM generation. Anyone has any doubt here? Okay, let me go to the next slide. Now let's discuss the demodulation of the FM. Okay. So the demodulation of the FM, we do it with the help of a circuit called differentiator. Okay. So what we do here is that we have a modulated signal where message is residing in this cos something, right? It is inside this cos argument. Once you differentiate this st with respect to time, what will happen that whatever is there in the argument of the cos will come to the amplitude of the cos. So after the differentiation, this cos will become sine. Actually, this should be sine here. Okay, and you have a omega c plus kf into id, and you have a in amplitude also you have omega c plus kf into mt. Now, if you see this signal, this complete thing, this actually looks like a AM signal. Why? Because here the message is in the amplitude also. Okay, so your message is there in the amplitude also, and because of that, you can say that it looks like a kind of AM signal. And since after the differentiation it is an AM signal, we can demodulate this differentiated signal just the way we did it for the AM signal, and that is by passing the signal through the envelope detector. Okay, so now after the differentiation, the signal is kind of now AM signal. So just take this signal and pass it through the envelope detector, and we'll be able to recover the message. Now again, for the envelope detector to work, this amplitude has to be always positive. Okay? So this is the one of the criteria for this demodulation to work. Okay. So the first step is differentiate the modulated signal that you have received, and after the differentiation, pass it through the envelope detector. Anyone has any doubt here? Let me go to the next slide then. So this is, I have just taken some of the differentiator circuit here. So differentiator in the time domain becomes the multiplication by j omega in the frequency domain. Okay. So if you have gone through the analog classes, this is the one of the example of the differentiator. Okay. This circuit is actually the differentiator. So when I say the differentiator, you can implement this differentiator with the help of this circuit. Okay. So first take the signal, modulate the signal as of t, pass it through the differentiator, and after the passing it through the differentiator, we'll pass it to the analog detector to get back the original message. Any doubt? Anyone? Okay. Let me go to the next slide then. So that was all about the FM and the PM. Let's talk about the new circuitry, which we all call as a super Hydrodyne receiver. Okay. So super Hydrodyne receiver is a bit like widely used in the radio circuitry, and let's go through how does it work. So when we are talking about the wireless communication, we will have an antenna at the receiver side. We are just talking about the receiver here. We are not talking about the transmitter. Okay. So the circuit that we are going to just discuss now is just a receiver circuit. So we have the antenna. After the antenna, we have something called what we call it as a RF. Okay. Because antenna is receiving a signal, which is a kind of RF, or you can say a radio frequency signal. After it receives the radio frequency signal, you have RF circuitry, or you can say you have a circuit which works in the RF frequency range and does do some kind of processing here. And after this processing, it goes to the mixer, and we have a local oscillator here. This mixer will down convert this RF signal into some kind of IF signal, which we call the intermediate frequency. And after that, it will be general detection technique, depending upon what kind of modulation we are using. This super Hydrodyne receiver that I am discussing now, it is irrespective of the modulation. Okay. So here we are just using the generalization here. It can be used for any kind of. So the circuitry that we use for the AFM and PM will come into picture from here onwards. Till this point, it is kind of independent of whether it's AM and PM. Till this point. Okay. So here you have a RF, which can be somewhat of gigahertz. After the mixer, you have a IF, which we call it as intermediate frequency, which can be some hundreds of megahertz. Okay. After that, it will go to the typical detection technique. Okay. Now, this mixer is actually the multiplier that we discussed in the DSPSC signal. You have the modulated signal multiplied with cos omega LOT, and you get back the some signal here, and then do some processing to get back the original message signal. So this mixer that you see, this is actually the mixer that we discussed in the DSPSC signal. Okay. Now, one thing to notice here is that if let's say we have a local oscillator here, we have an input signal which carrier frequency is omega c. So once you down convert it, okay, with the help of this mixer, the signal will have the frequency equal to omega c minus omega LO mod and omega c plus omega LO mod. Okay. Now, this is what we want to pass through this filter, and this is the one we want to get rejected by this filter. Okay. Now, this omega c minus omega LO is some frequency which we call it as the intermediate frequency omega IF. Okay. Now let's take another case where we have a MT, some other message, let's say GT cos omega 1t. Okay, and after the down conversion, we are getting a signal which is equal to omega c plus omega 1, and we are getting omega 1 minus omega c. This two signal we are getting. This signal will get rejected by band pass filter, but if this signal, which is omega 1 minus omega c, is equal to omega c minus omega lo, in that case, this signal will also pass through this filter. Okay, so the condition here is that omega c minus omega lo is equal to omega 1 minus omega c, or you can say that 2 omega c is equal to omega lo plus omega 1. Okay, so if we have this criteria for the signal, that signal will also get down converted to the same omega if. So this is also equal to omega if. Okay, so we at the input side we can have a two different kind of signal which can get down converted to the same intermediate frequency, which is omega if. Out of this two signal, one of the signal that we want to receive it, but other signal we don't want to receive it. We don't intend to receive that signal. But there is no way we can remove that signal, because that signal will also pass through this mixer without any kind of attenuation or rejection. Now so one of them is wanted, one of them is unwanted. So unwanted signal, we call it as an image frequency or image signal. Okay. So this image signal is always the unwanted signal, and we don't want it to be down converted. Okay. Now why we call it as an image signal? So answer lies here. So let's say this is omega lo. Okay. And let's say that we have a omega c, which is somewhere here. Okay, this is omega lo, this is omega c. The difference between these two, we call it as a omega if, intermediate frequency after the down conversion. Now if you see the image will have an equal distance with respect to omega lo as it has a distance with omega c. If you see, the distance between omega c and omega lo is same as distance between image and omega c. Okay, so in this case, oh wait, there is one thing wrong here. This is lo, this is lo, this is lo. Okay, so the distance between lo and omega is the same as distance between lo and omega image. But the thing is that both has a, so here omega c is more than omega lo. Here omega lo is greater than omega image. So image will have to be somewhere around here, which will be giving us omega image. So if you see this omega image, it also has the same distance with omega lo, which is omega if, and that's why it is getting down converted to the omega if. Now if you see, draw a vertical line here, omega image is kind of mirror image of this omega c with respect to this vertical line which is around this lo. That's why we call it as an image signal. Okay, so this is the super Hydrodyne receiver. We call it as a super Hydrodyne receiver because here when we are done converting it, we are not converting into the DC. So if you remember the DSBSC demodulation, when we down convert it, omega c and omega lo has the same frequency. And once they have the same frequency, it gets down converted to the 0 or DC, centered around DC. But in this case, we are down converting it into such a way that instead of getting down converted to 0, it is getting down converted to the some intermediate frequency omega if. And that's the difference between the receiver that we have seen is the DSBC and this one. And this kind of receiver where we don't convert it into the DC, but we convert it into some intermediate frequency. We call this circuitry as a super Hydrodyne receiver. Okay. Anyone has any doubt till this point? Okay. Let me go to the next slide then. So here it is just a graphical representation of the image and the lo and the our this like RF signal, the signal that we want to receive. So there are two scenarios here. In both scenario, omega LO will be kind of centered. In one case, image is more than, has a value more than omega c. In second case, omega c is more than image. Okay, but one thing is same is that distance between omega LO and omega c is omega if, and distance between omega LO and omega image is also omega if. And the same thing is here. Distance between omega LO and omega c is omega if, and distance between omega image and omega LO is omega if. Okay? So in the first case, omega LO minus omega c is equal to omega im minus omega LO, and which is equal to omega if. But in the second case, it is just opposite. It is omega c minus omega LO is equal to omega LO minus omega im is equal to omega if. Okay, so in both cases are super Hydrodyne receiver. It is just that in one case image is higher, in second case image is lower. Okay, but in they both case it is a image, because if you draw the vertical line here, omega image, this image is mirror image of the omega c, and when you draw the vertical line here, this image is actually the mirror image of this omega c with respect to this vertical line. That's why in the both cases this omega im is the image frequency. So omega im is the signal which we don't intend to receive, and omega c is the signal that we intend to receive it. Okay. Now, how to make sure that this omega im we don't receive it? Okay, so if you remember the architecture, we had first antenna, after that we have RF, and after that we have the mixer. Now, this RF plays a role in removing or attenuating or rejecting this image signal. So we have to design this RF such a way that it amplifies the intended signal, but at the same time it reduces the or attenuate the or reject the image signal. Okay, so this RF circuitry has to be kind of selectivity circuit, which means that it select only a certain frequency range to pass it through the output and reject the rest of the frequency. Okay. So this RF plays a part to reject the image. So you have RF circuit here, both omega im and omega c signal are incidenting on this antenna, and then this antenna will, after the antenna it will reach the RF, but RF will reject the image and pass only the signal which is around omega c, and then it will get to the mixer or the down converter, okay, which will down convert it to the omega if. Anyone has any doubt till this point? Okay, let's go to the next slide. Now, here is the question. So here it is asking that one of the main function of the RF amplifier in the super Hydrodyne receiver is, so first is to provide improved tracking. RF amplifier doesn't care about the tracking. Okay, this option is not correct. Permit better adjacent channel rejection. Increase the tuning range of the receiver. No. Improve the rejection of the image frequency. This is the option. Okay. So just like we discussed in the last slide, with respect, so here you need to remember that here we are talking about this RF amplifier with respect to the super Hydrodyne receiver. Okay. So for the RF amplifier for the super Hydrodyne receiver should be such that it rejects the image frequency, and that should be the correct option here. Anyone has any doubt here? Let me go to the next slide there. Okay, so here we have a problem. So a super Hydrodyne receiver, if intermediate frequency is 450 kilohertz. So here we are talking about FIF, which is, so I'm not writing it as omega IF, I'm writing it as a FIF, which is equal to 450 kilohertz. The signal frequency is 1000 kilohertz. That we are talking about the incident signal at the antenna, or the signal that we want to receive, or the desired signal. So FC is equal to 1000 kilohertz. Then the local oscillator frequency and the image frequency are respectively. Okay. So we have this local oscillator, we have this FC, we have this F image, and the difference between FC and FLO is omega IF. Okay, now instead of writing omega F, I will write as a FIF. So this is one of the scenario. Another scenario is just opposite of this that we discussed in the last slide. There can be two scenarios. FLO is again at the center, but image is here and FC is here. Okay. And again, this is FIF, and this is again FIF. Now, let's take the case when signal frequency is 1000 kilohertz and it is here. This is 1000 kilohertz. This is 450 kilohertz, which is intermediate frequency. Since this distance is 450 kilohertz, and this value is 1000 kilohertz, the value of FLO will be 550 kilohertz, and value of the image will be equal to 50 minus 450, because again you have to go back by 450, and that will be 100 kilohertz. So the local oscillator frequency we are getting it to be 550 kilohertz, and image frequency we are getting to be 100 kilohertz. So do you see any option correct? No, it's not there. Now let's go to the second case. Again, in this case, FLO will we need to find out, and FIM we need to find out. FC is given as 1000, and this distance is given as 450. So in this case, the FLO will be equal to 1450. Okay, so this will be the FLO. So FLO is, so this option is wrong, this option is wrong. So we have 1450, 1450. Now let's talk about the image. Image will be again further 450 from the FLO. So it will be equal to 450 plus 450. 1450 plus 450, which is 1900. Okay, so this will be the correct answer. Anyone has any doubt here? Okay, if no one has doubt here, then we can stop the class here, because I have this much only for the today's class.